So this is carbonyls and some other kind of compounds, like you have alcohols and ethers, carbonyls. You also have acids and other stuff. Okay, so first thing, acid catalyzed acyl exchange called AAC2. Okay, so what happens is that if you have this kind of ester over there and you treat it with H plus, you will get this thing. Okay, and then after that you can add HOR3 to it in the slow step to get this thing. Finally you do a proton shift, and after that you you just release that, like that, and that will give us HOR2. So see, a proton shift, so this H goes to there. After that this thing leaves, and the lone pair of the oxygen, those satisfy the carbon's valency, and from that you have this thing. And from there you can remove that H plus and get this thing. So essentially what happened is that you changed this ester into this ester, so from R2 to R3 using acid, right? And this is AAC2. Why C2? Because it's bimolecular, right? So look at this. The slow step is this thing where you are taking the concentration of this species and HOR3, but the concentration of this species will be the same thing as that because this was a fast step, right? So that means it's bimolecular. Okay, it could also be AAC1, where you first of all proton it and make it leave, forming this this kind of species, which is, I mean, it's relatively stable. So like it's the acyl thing but a carbocation. Okay, and then treat it with HOR2. So in this case this would be the this would be the slow step, and just have the original ester basically hydrolyzing, right? So in that case this rate would just be dependent on the concentration of the original ester. Yes, that looks correct. Okay, so this is for acyl exchange. You also have alkyl cleavages. So for example, like this, right? So in this case this this OR2, that bond is breaking. This is the alkyl bond. So that breaks and you get this thing. And then R2 plus H2, that is ROH. So this thing, alkyl cleavage, this is like, if you want to reverse this reaction you can do that as well. Okay, then you have base catalyzed acyl exchange. Cool. So that's pretty straightforward. It's basically just SNAC, right? Base catalyzed nucleophilic substitution, then addition and elimination mechanism. Okay, next, base catalyzed alkyl exchange. Okay, so that's like SN2 basically, pretty much like that. Oh no, wait, this is like SN1 and this thing is like SN2. PAL2 is SN2 and this thing is SN1, right? So this R1COO minus thing, that's like a good leaving group, so basically just R2 plus that's generated, and then from there you can hydrolyze to get this thing, or solvolyze. So R3OH would be the solvent in this case, and that will give us this thing. Okay, same thing can be done in reverse order as well. So that will convert this R1COOR3 to R1COR2. Okay, BAL2. So base catalyzed alkyl cleavage or exchange, but bimolecular, right? So this is what's happening. Now this is like proper SN2. Cool. These mechanisms also work for some other polar double bond containing molecules. Okay. BAC is a special case of acyl nucleophilic substitution, which is the same mechanism but with generic nucleophiles rather than OR minus, right? So nucleophilic addition, that's another reaction that carbonyls show. So there are like two different mechanisms. Acid catalyzed, you will just protonate this oxygen over there and then you would add the nucleophile and get this thing. So this is called hemiketal, where you have R1 and R2 attached to the carbon. So you will have ketal in that case, and when you have R1 and H attached to the carbon, you will have acetal. So like over here, this will be hemiacetal, and when this OH is replaced by OR2, that will be a proper acetal, not just hemiacetal, acetal. Okay, very cool. So protonate it, and then after that take this R3OH as a nucleophile, and yeah, and then after just hydrolyze this thing or do something like a proton shift. Well, okay, not a proton shift because you have treated with the H plus, so you have to hydrolyze it. Okay, so after hydrolyzing, this will just turn out of this thing. Okay. Yes. So this step over there, this is actually the elimination steps. This would be the exchange step, but only till this step is it addition. After that, this would be addition elimination, which is basically substitution. And you can do the same thing over here as well, right? So after you have eliminated this thing, you get this, and then you can do that thing, right? So first add, you just get hemiketal, and then do SNAC, you get first add, you get hemiketal, then eliminate, and then add, you get ketal. Same thing, base catalyzed, right? That can also be done, which is a much simpler process. Yeah, so it's like SNAC, but you stop midway and you just hydrolyze this thing. Cool. RSH also works similar to ROH for these reactions till now. Yes. So R2CO, okay, CHO plus R1SH. So this will be called thiohemiacetal, thio for sulfur, and this will be thioacetal. Cool. So yeah, that's like the proper basic introduction of the reactions of carbonyls. Now some common mechanism of alcohols and ethers. So alcohols are famous for dehydration, right? Ethers also do those reactions. So just treating it with acid, that will hydrolyze this thing. And yeah, so that will generate H2O somewhere. Okay, so H plus protonate, then cleave the bond, OR2 bond. This will be R2 plus over there. This thing is gone, R2 plus, yes, yeah, that was it. So that's the first reaction, and then you could also do this thing, right? Cool. Hey, that looks pretty much like the second step of acid catalyzed. Well, alkyl cleavage, I don't know. Yeah, looks like that. Okay, whatever. So these mechanisms are very predictable. It's just that you protonate the oxygens and then you cleave the surrounding bonds, and you get different products depending on what bond you cleave. And there are some other factors that affect which bond gets cleaved, and yeah, but we will not talk about that. Okay, the leaving R plus must be H plus or more stable than H plus, or reaction will not proceed. Instead of H plus, we can use more effective Lewis acids to do the same. Cool. So SN1 and SN2 after protonation, that's also a common mechanism of alcohols. For example, with acid, the hydrogen halide acid, right? With those, these show this mechanism, SN1 and SN2 after protonation. Cool. Acidity of carbonyls. So carbonyls, well, at least carboxylic acid, that's pretty acidic. Well, the reason for that is that the charge will be an oxygen, which is like very electronegative, plus it is resonance stabilized. So the stabilization of the charge due to resonance, that's the main factor why this is why the conjugate base will be stable and you will have acidity. Same thing can be said for alpha, yeah, for alpha hydrogen carrying carbonyls, right? So for example, this thing. Wait a second. Yes. So look at this thing. After removing this H, you will get this conjugate base, which is resonance stabilized. So even these kind of ketones or aldehydes, they can also have acidic hydrogens. So now what factors affect this acidity? The hydrogen atom on the hydrogen atoms on the atoms next to carbonyl group are acidic because the deprotonate form is resonance stabilized. Groups that resonance stabilize the carbonyl in acid and uh, in acid or don't stabilize the negative charge on deprotonated form by resonance. Wait, what? Wait, this sentence is not correct. Groups that resonance stabilize the carbonyls in acid or don't stabilize the negative charge on deprotonated form by resonance. Oh, this for is not supposed to be there. So groups that resonance stabilize the carbonyl in acid don't necessarily stabilize the negative charge on deprotonation, right? So for example, in this, the thing is that this original molecule is resonance stabilized, but after removing the H over there, this negative charge that's not resonance stabilized by this alkene, by this pi bond between carbon carbon. Instead, it's only resonance stabilized by that carbonyl group. So what that means is that resonance stabilizing groups, those don't increase acidity, they decrease acidity. Okay. So resonance reduces the acidity as it promotes formation of acid instead of salt. Minus I effect still increases acidity, and that's why phenyl and alkene groups increase acidity even though they do resonance with the carbonyl. Okay. So preparation for alcohols and ethers, you have these things. First, you can oxidize some kind of tertiary alkane, and yeah, it only happens with tertiary alkanes. It doesn't happen with secondary and first degree. Okay. Then Rx plus OH minus, that's pretty obvious. OR2 minus, that can also be used. Cool. Then alkene and acid, right? So low concentrations of the conjugate base of that acid, right? If that's there and there's still a considerable concentration of H plus, for example, if you use something like AlCl3 and HCl, the Cl minus will get absorbed by LCl3 and the H plus that will not be. So that H plus will add to the alkene, and then the solvent will add to the alkene. Cool. So that's what happens. And in case the solvent is ROH, you just get OR. So over here it should be ROH and OR in the more general case, but H2O works very fine. So oxymercuration, demercuration. All right. Yeah, that's also one way of doing it. So oxymercuration, that will give something like that. Okay, fine. This works, no big deal. Hydroboration oxidation. So instead of hydroboration oxidation, yeah, fine. BH3, yes, that will hydroboronate that with THF as the solvent. H2O to OH minus, right? That's nice. Instead of BH3, which exists as B2H6, We can also use SiA2 BH or NBBN. So these names are weird. So B2H6, we know it's just diborane. It's used frequently for hydroboration. These two other remaining things, so SiABH, it's this thing. So dicyamyl borane. So this SiA thing is for cyamyl, and for that 2 thing is for di, and BH borane. Cool. And 9BPN, it's also some kind of diborane, but much more bulkier. Yeah, fine. Next, ozonolysis. Okay, looks correct. So this is like reductive ozonolysis. Cool. Mild oxidation. Okay, so OSO4 is a mild oxidizing agent, and NaHSO3. Okay, we don't exactly know what the purpose of that is. It doesn't matter. In the end, we know what the reaction does, right? That's all we need. This thing is called glycol. Okay, KMNO4 OH minus, cold KMNO4 OH minus. That would also do this thing, right? Hot acidified KMNO4 that cleaves the whole thing. So we don't want to be using that. Okay, Woodward and Prevost dihydroxylation. So the first steps are almost the same. You just have this thing with I2 over there. You form this thing which has an OI bond which is weak, right? So from that OI bond, you can do some stuff. You can add that to alkene because of that weakness, right? It's like polarized enough to do that, right? Yes, that's correct. So notice that only only iodine is used over here. Why? Because when it adds, right, so it will add completely, it will become this thing. After that it will be like that, and basically this I minus, it's removed, it's completely removed, and guess what, it will yeah, so Ag plus and I minus, like AgI, that will precipitate because it's not in the reaction mixture initially. So there's the pathway for iodine to get removed. So that's the thing that will drive this reaction forward, the precipitation of AgI. Okay, so after this step you have this thing, right? So H2O adds to that, right? So actually we saw this mechanism before as well. So this adds, it becomes this thing, and then after that proton shift, and yeah, after proton shift it will break, right? These lone pairs will jump to the positive charge carrying oxygen, giving us this thing. Cool. Remove the H plus over there, you will get this thing. Then OH minus, base catalyzed acyl cleavage, right? Cool. Yeah, that looks correct. Okay, that will give us this thing. Fine. So notice it's not base, it's not like SN2 that OH minus just comes over there and takes it out. No, it is a different mechanism, and that's why this stereochemistry is syn. So Woodward is syn dihydroxylation and Prevost is anti. So in Prevost, what happens is that after this is formed, this guy just does SN2 directly, right? So directly SN2, and that gives us this thing. And then after that you use OH minus to do BAC, and it gives that thing. Cool. So notice the difference in the conditions over there. Over here you are using H2O, so you are using the water molecules to do this thing. Over here you are using the carboxylate molecules to do this thing. So yeah, that looks about right. So for example, if I chose something like an organic solvent, then maybe this is what will happen. And if I chose a polar solvent, right, so H2O, then this is what will happen. That looks about right. Okay, cool. Okay, then the next reaction, yes, this thing, epoxidation. So epoxidation is generally done with MCPBA, right? But it can be done with any peroxy acid, and yeah, that's how it happens. It just epoxidizes this thing, and then if you put the epoxide in a polar protic solvent, this will this will solvolize to give you something like this. So in case it's H2O, you will get this anti-hydroxyl thing, whatever this is. Okay, cool. Then NO2 minus and H plus, that gives NO. Oh, yes, diazepam salt. And after forming the diazepam salt, treat it with H2O, and yeah, that will kick away the N2 and it will leave the reaction mixture, making the reaction go forward. Cool. That's nice. Prince reaction. So this is a big mechanism over there. Okay. So what's happening? Okay. You have this formaldehyde. You treat it with H plus over there, and you form this thing, and then you attach the alkene to it. Okay, cool. So attaching the alkene seems like that. Cool. So this little part is the formaldehyde, and this is the alkene attached over there. Yeah, that seems about right. Cool. And the alkene, it's a terminal alkene, so it has that hydrogen over there. Cool. And then there are like 3 pathways over there. One pathway just leads to this, yes, where you just lose this H plus, right? So it's like E1 mechanism, and you just get this thing. Okay, that's something that could happen. What else could happen? Yeah, what else could happen? Okay, so you could just take OH from the water and get this thing, right? So that's another thing that could happen. And then H2O. Okay, looks cool, right? So you just took OH from the solvent, so you will have this thing in that case. So these two are not that extraordinary, but the last one, this green one, is the more useful thing. So this formaldehyde, the oxygen attaches over there, and you get all this. Yeah, right. This is a okay, fine. So that does this thing, and then you got this. So this is a primary carbocation, very unstable, but in fact it will be like very short-lived, and immediately oxygen will attack and you will have this, and after that you got this thing. So yeah, that's Prince reaction. And you also have this thing. Oh, this is very strange. It won't form. So this 6-member ring thing, that's what we want to form, because these things, they're not really that special. Okay, so what's the basic thing that we did? Took formaldehyde, treated with H plus, took any alkene, added the formaldehyde, the protonated formaldehyde, to this thing. Okay, and once again added a formaldehyde to that thing, and then after that you did something like an intramolecular rearrangement kind of thing. Okay, so this oxygen just uses its lone pair to attack that carbon over there. Okay, that looks about right. So those are the 3 key steps over there. Cool. That's going to be Prince reaction, huh? Fine. I don't think that will be asked, right? It looks complicated. Next, catalytic hydrogenation of carbonyls. Okay, so carbonyls are somewhere over there. Okay, fine. So acyl. Okay, fine. I'm getting it. Acyl halides, those are pretty reactive. After that you got alkyne, then you have aldehyde, and then alkene, then this guy. Fine, I will memorize this later. Okay, nucleophilic addition to carbonyls with Grignard reagent and hydride toners. Yeah, that looks correct, right? It's just R minus inside and then nucleophilic addition. Cool. Reduction by metal and acid. Yes, yes, that makes sense. Cool. Yeah, that looks correct. That looks correct. Proper reduction. Nothing so special. Bivalent metal. Fine. So this is for the univalent metal case. And for the bivalent metal case, you have these combining, right? So these radicals form, they might combine and form this thing, and then you hydrolyze that, so you get this thing. Cool. So it's, yeah, it doesn't have any specific stereochemistry because these can combine in any way, right? So bivalent metals do these kind of things and univalent metals do this. So this will be like the major product. Yes. Cool. Next question. Marvin Pondroff Worley reduction, MPV reduction. Okay. Yes, this thing. This is like important. So first you take the carbonyl and Al and whatever this compound is, 3 times of that. Okay. After that, yeah, you do the usual thing, right? So there's a hydrogen over there in the carbon. This is kind of weird because the hydrogen is not directly attached to aluminium, and yet it does that, right? Yet the hydrogen does get removed, which, yeah, it just looks weird to say the least. So cool, that hydrogen will get removed. So once that happens, you just get this thing, okay, and then from that you can get that. Okay, so the major step over here is that this oxygen coordinates with aluminium. After that, a hydride shift takes place to the carbon directly, and after that you remove this, you remove one of the formaldehyde things, and not formaldehyde, whatever this thing is, you remove one of these uh, propone things, you get this, okay, and you use another thing from the solvent, right? You use this thing. Oh, so this is the solvent that we have uh, propanol as the solvent. Cool. So then it attaches once again, and then once again you do a hydride shift. Oh wait, not a hydride shift, in fact it's a H plus shift. Wow, that's weird. Okay, I mean it's not weird because look, the oxygen, it's closer to aluminium and then that has hydrogen attached to it. Yeah, yeah, over there it was the carbon that had hydrogen attached to it and stuff, so that was a little different. Anyway, what does it do? It protonates that thing, okay, and then it leaves, right? Then this thing, this bond cleaves, and yeah, the lone pair goes to the oxygen, so you have this thing. Okay, so this reduction is weird, but it does happen. So okay, 15th. Right, so it's just AlH4 minus reduction, so it's a good hydride donor first of all, so that will you just, yeah, that will just use the hydride. Oh yeah, this is one of these special cases where it does not directly use the hydride to attack the carbonyl. In fact, it uses the hydride to form H2 and liberate it, and that's the driving force of the reaction. Cool. Not all hydride donors do this, alright? Yeah, that's not always the case that you will just form H2 and release it. No, that's not always the case. As we saw, for example, yeah, how the carbonyl, right? So not amide, just the carbonyl reacts with AlH4 minus. It would just take the hydride and put it on the carbon. Easy as that, and then take something from the solvent. That will just do it. And the aluminium hydride, that will also get reduced, that will also get converted to Al OH 4 minus. Cool. So what's happening over here? Over here, hydrogen is getting liberated. Okay, then you have AlH3. Yes, so this atom, okay, fine, resonance over there, you got O minus over there. Then coordination, and then once again you have this H minus transfer, right? So H minus transfer, you get this thing, okay. Then it comes down colliding and kicks away this. So you have this imine thing over there, and then once again that get reduced the proper way by hydride transfers. Okay, so hydride transfer, you get NH minus over there and then H2O, this thing, right? So this is the proper way of how things happen. This is kind of an exception, right? Okay, next. Yeah, cyanide and ALH4 minus. So yeah, first thing first, just hydride transfer this thing. After that it attaches itself to that. Okay, once again a hydride transfer, so it can in fact, oh that's nice. And yeah, and then you need something from the solvent, so you took that, right? So H2O. That seems weird. Fine, so it is in fact H2O that we are using. Yeah, it does that and you get this thing. So right, and then once again you have this thing, it leaves, and then you just have R, this NH minus. Okay, that's weird, but that happened. Fine, and then it leaves and this happens. Cool, not a problem. Yeah, that seems about nice. So this will get reduced to this thing. Fine. Okay, carbon monoxide plus H2, CH3OH. Doesn't look very bad. C2O3. Okay. Hey, C2O3. No, wait a second. C2O3 was something else. It should have been Cr2R. Or not. How is C2? Oh, wait. C2O3 is something like a peroxy acid. Ah, yes. That makes sense. That could be the thing. C2O3. Carbon oxide. Yeah, looks like that. O3. It must be something like a peroxide. Is it not? Anyway, carbon monoxide plus H2. That just gives CH3OH. Okay, that's not a problem that carbon monoxide plus H2 gives this thing. But why is this C2O3 molecule involved over there? Or is this supposed to be something like Cr2O3? Maybe it was Cr2O3, who knows? Again, this reaction, I don't know much about it. Okay. ROH plus CH2 minus and then plus. Okay, this thing is a diazine salt, so probably just N2 that will get released. So it's just, yeah, just CH carbene, something like a carbene, not exactly like it though, right? So it probably is going to do that, right? It is probably just liberated by the oxygen attacking the carbon over there. Okay, so first what happens is that it acts as a base and takes that away, and then after that it attacks the carbon. Cool. And then you have ROMe plus N2. Looks about nice. 16th reaction, I don't know what it's supposed to be though. Yeah, whatever. BH3 reduction of acids. Yeah, this is one of the more important reactions. Yes, I mean the mechanism is not important, but it basically gives the reasoning that why BH3 is able to reduce acids and not anything else. It does not very easily reduce other things, right? So the whole thing that why it does that is because of these transition states over there, for example, right? Look at this transition state over there. So basically you are generating H2. Yeah, well, that seems about right. You are generating H2. So the hydrogen generation, that's why BH3 can reduce carboxylic acids. Okay. Even though it cannot reduce most of the things. Fine. So first you just coordinates and you have this thing created, and after that the hydrogen is removed. After that you have this thing. Okay. Well, this is weird. Hey, what happened in this step? What did this BH3 do? OAC2. Okay, wait. Something's not right about it. Oh, so yeah, it did the same thing with others as well, and that's why I got this thing. Fine. And what's with that BH3? All right. Something's very weird about it. How did we got an alkene and why? Why is this even happening? Yeah, something's about not right about it. There should not be an alkene out of nowhere. Right? Oh, sorry, this is the wrong step. This is the right step. Okay. So after this thing you have this. Okay, H2. Yeah, that's why. H2 generated, and then you have this. Okay, BH3 minus over there. These are still coordinated to it. And then you have this alkene already. Okay. After that there's a hydride shift, and because of that you have this. Right. So that's cool and all, nothing's bad till now. And sure, so you have this thing. Okay, you have this kind of species, and after that the real main steps start. That this reacts with that. The oxygen, it combines with that in this case, giving us this weird thing. And then there's another hydride shift. Okay, so the mechanism in short is very complicated, to say the least. Oh, and then this thing happens. Okay, cool. Right, so H2O attacking this thing is justified because it will just attack. There will be a proton transfer to the oxygen, and then after that it will cleave. So the bond between oxygen and boron, that will cleave. Cool. And you will get this thing. Right. Yeah, that's in this scheme. Proton transfer, this will cleave, you will have this. Right, which basically is this thing. So that's not the problematic part. The problematic part is this little step. So the third step. Once you have formed this species over there, right? After that, what happens is that the oxygen over here when it's not coordinated, it attacks the other boron. So this oxygen is bound to two different borons, and then this oxygen attacks the other boron over there, forming this weird cyclic transition state. Okay, so this oxygen is like over there and this oxygen is over there. Cool. And then once again just have another hydride shift over there, right? And yeah, the hydride shift just releases this bond over there. Cool. Yeah, that seems correct. So could it have happened directly though? The way they teach it in most places is that this happens directly. The H minus just shifts to the carbon, kicking out this OBH group. It does not in fact happen directly. It happens through this weird mechanism. But yeah, I mean, like, you could say that it even if it happens directly, it's still giving the same thing. So yeah, whatever. Yes, that explains that why this can reduce carboxylic acids and not anything else. So this part, after the release of hydrogen, it's okay, it's not that bad, it's nothing like new. But the release of the hydrogen, that's a reaction that drives it forward. It cannot do the same thing for ketones or aldehydes, right? It can only do this for this thing, or for alpha, uh, yeah, the alpha hydrogen, right? So the carbonyl carbon, the next carbon, the hydrogen attached to that carbon, that hydrogen is acidic, so it can do this thing for that hydrogen as well, probably, but maybe not so effectively because it's not that acidic as carboxylic acid. Okay, anyway, next. This is obvious. Okay, 2ROH gives this thing, fine. Carbonyls. Okay, HOX plus X minus, fine. Oh yeah, this is that kind of oxidation. The hypochlorous acid, the hypohalide acid oxidation. Yes. So in this case, HOX acts as an acid as well as a nucleophile. Yeah, that's what it does. And it gives this thing. And after that the negative, yeah, the base takes away that H over there and then it does this thing. Okay, so you just have to have a halogen and a really strong base, or maybe just a good concentration of OH minus. That will do it. That will do it for you. Okay. Oxidation of alcohols, the usual methods, yeah, sure. That's one way to get carbonyls, right? What is this? Oh yeah, that's the reaction that I was talking about before. Uh, that when you run this over a metal surface, the hydrogens can be removed. So this dehydrogenation just gives ketones, okay, or aldehydes or carbonyls. Hydrogenation of acid halides or acyl halide. Right, this also happens. Not a big thing. Okay, so the catalyst that we use is Ronstman's catalyst, that makes H2 less reactive so that it does not hydrogenate the aldehyde as well, right? Okay. Oxidative ozonolysis, that will work, no big deal. Oxymercuration, demercuration, yeah, sure. Stephen's reaction. So reductive ozonolysis, that gives alcohols. Oxidative ozonolysis gives carbonyls or carboxylic acids in cases when you have hydrogen. Stephen's reaction. Okay, so cyanide, HCl, SnCl2. Alright. Oh, that's kind of weird. This SnCl2. Why did this turn out to be radical mechanisms? So, and then HCl. That's weird. SnCl4 over there. What is this? I mean, okay, not a big deal, but still, it's weird. Right, so this HCl thing, it could also have been like that. No, it would not have been like that. Yeah, that's right. Fine, this makes sense. This makes a lot of sense. Then HCl, and you get this weird thing, SnCl6. And yeah, so this is the main thing that you have to look at. Cool. And then after that, you remove the SnCl4 and you treat it with H2O, and this thing happens. Okay. Oh, so now after this point, it's just the hydrolysis of this imine, which is an easy task. So this is not really that special, right? The only thing that was special was the 1, 2, 3p thing. So cyanide and HCl plus SnCl2, what does it do? First of all, HCl, it adds to the nitrogen, okay. Then SnCl2, it adds to the carbon, and then there's some kind of free radical mechanism. Yeah, okay, cool. And then after that, you deal with HCl once again, giving us SnCl4. I don't know what's happening in 3b to 4 step. What even is happening? Come on, think. Can't it just be that it was some kind of anion over there? Yeah, that's exactly what happened over there. Oh, alright. So maybe it was something like this. Okay, cool. Start like that. So you have this R, NH, SnCl3, and now HCl, you will add it over there, positive charge. You got chlorine minus over there. It will attack it like that, kicking out this bond. So this will be R, NH2, right? So this will be minus over there, and plus, wait, that's not making sense. That's not making sense though. So that's not what happens in that case. What is happening? What even is happening over there? Chlorine minus. Oh, so this might be a better way to think of it. The chlorine minus is roaming around. It just attacks Sn over there. Okay. There was this already formed bond over there. Cool. And now you have this thing, SnCl4 minus. Cool. Yeah, that probably is better. Okay. And then that might be released. Okay, and then you also have this H plus roaming around. Cool. Now this only makes sense if something like this is actually in the species. It's actually in the reaction mixture, which it's not there. It's not there. This would be not correct. So then what is happening? Why did they only use 1 electron and not 2 electrons? Yeah, you should have just given up the whole lone pair. Why make it happen in 2 different steps? Okay, so probably that is what happens, right? Because this is from Wikipedia straight. So that is what happens. You just get this RNH. Yeah, that's what will happen. That's what will happen. This will be there, minus, and then plus over there, and then this Cl minus over there, it will attack. Cool. And that's why you have this. Okay, it's not a radical mechanism, it's just that they showed the electron transfer in two different steps. Fine, no big deal. Yeah, that looks correct. Okay. And then what? After that it's all the same stuff. Cool. And the eighth one. Fine, it's the same kind of thing that always happens, right? The same thing happened with BH3 as well and other compounds as well. Yeah, the lone pair containing guy just attacks the aluminium. Hydride shift takes place, right? And then after that, some solvent molecule comes in and it provides hydrogen and also promotes the leaving group to leave, which in this case is this ALOH and ibutyl 2 thing. Cool. So it leaves, and once again you just got an imine, and after that imine just hydrolyzes, so you will get an aldehyde in that case. Okay, Itard reaction. Okay. Oh, that's nice. So now I finally have an explanation of why why the benzyl position can be oxidized so readily, because the nearby pi bonds are in fact involved in this oxidation. Okay, cool. So first of all, it just attaches itself nearby to the it attaches itself on the aromatic system. Okay, doing this thing. There's also some kind of proton transfer. Yes, looks like that. Okay, cool. Right, this must be what's happening, that this is attacking it directly, making that O minus over there. There's still that positive charge over there. Okay, and then it gets that hydrogen, right? So this is like 2-3 steps condensed in one thing. Fine. After that, what happens? Okay, after that it attaches to that. That's weird. Oh, so it changes the position. Oh, that's clever. Wow, that's a nice mechanism. Fine, so it attaches to the carbon, and in the same time it's moving that pi bond and cleaving the chromium carbon bond to form this thing. All right, and then what? Okay, then this thing happens. The oxygen's lone pairs, they attack the chromium, kicking out the chlorine, but the chlorine takes the hydrogen as well, and taking that hydrogen, it creates a negative charge on this guy. So from that point it can just leave, right? Okay, maybe that's not what happens. In fact, maybe it's not like that, but that should be the thing, right? The oxygen's attacking. Yeah, oxygen will attack this. Okay, creating a positive charge. Cool. Kicking out the chlorine. Okay, till that it's fine, and then oxygen will retract its bond, and then the chlorine will take the hydrogen, creating the negative charge over there, and that negative charge will, through oxygen, kick out this CrClOH, and that's what happens. Cool. And so you just get this aldehyde. Well, that's really nice. That's nice. And then from there it's easy. From there just put just put another equivalent of this thing, and you'll just get yeah, you'll just get carboxylic acid or benzoic acid. Is that what it's called? Yes. Okay, that was nice. And then what do we have? So same thing with CrO3 as well. Let's see if it's the same kind of mechanism. Once again it attaches in a similar way. After that, oh, so there's something else that we can use over there. There's this anhydride that reacts. Okay, that's weird. So after the anhydride reacts, you get this thing. All right. Huh. I mean, this is weird, but yeah, whatever. So the anhydride reacts to give us this thing, but it also kicks off that. How? Right. So while it's attacking, it kicks off that thing, and while it's kicking off that thing, it also, yeah, the kicked off guy, that also takes some other stuff with it. Right. So you can see the lower part of this anhydride is just not there anymore, because it got consumed by this thing that got kicked off, right? CrOOH. Right. Similarly, second time you have another anhydride over there. Cool. And then H plus, acid catalyzed acyl cleavage. Okay. Yeah, that looks correct. Yes, that's correct. Acid catalyzed. Hey, is that even acid catalyzed? Okay, wait. Something's not. Right, it looks like that. Huh. Wait a second. Just wait a second. Let me think. That H plus over there. That bond over there. How did that happen out of all? Right. That does it. The carbon. Right. H plus over there. That leaves. Just get this. Yes, this is correct. It's just acid catalyzed acyl cleavage to get this. Right. So just do it on one anhydride thing first, and after that it will become clear that you are going to get something like a diol. Basically. You won't get it. In fact, you are on the path of getting that, but the diol just gets converted to this aldehyde. Cool. So that's this mechanism. Then you have this thing. All right. Yeah, this looks very normal. Okay. Gattermann-Koch reaction, basically Friedel-Crafts acylation. Okay. Carbon monoxide plus HCl gives this thing. Oh yeah, this is a reversible reaction. Or this thing. Huh. Okay, cool. Yeah, this looks fine. Whatever. So the AlCl3 just serves the role of creating an opening for the phenyl to attack. And after that it's done, it just goes away as AlCl3. That O minus it collides down to kick out the Cl minus, and then Cl minus will get consumed by AlCl3. Cool. So this is called Getterman-Koch reaction. Fine. RMGX Grignard plus CdCl2. Okay. Gives R2CD plus Mg2 plus X minus Cl minus. What? Okay. R2CD. Wait a second. What did we say? RMGX. So R minus basically. CdCl2. Oh yeah, this is not bad. This is not bad. Cool. And then this R2CD thing, that's what we are using. CdCl2. Ah, right. So this chlorine over there. That's nice. Okay. R2CD has very less reactivity as a carbon and donor, and reduces acyl halide to ketone only. All right. So this is a carbon and donor. Fine. Okay, this looks fine. No big deal. Okay. So what they mean by it has less reactivity as a carbon and donor means that it does not do nucleophilic addition anymore, right? Okay. Next. Right, this reaction is pretty normal. Okay. Hydrolysis of amides, cyanides, etc. We know the mechanism. RNG plus CO2 gives this thing. Fine. I have seen that a lot of times. Specific reactions. Okay. Oh hey, we had this kind of a thing somewhere. Yeah, but over there it was with formaldehyde, right? And now we are not using formaldehyde. We are using this this diol thing. Okay. And we are just treating with catalytic amount of H plus, so this gives this guy, and then it attaches. Oh, we are using something like that, huh? That's kind of weird. Okay, cool. Fine, so it creates this thing. So this is cyclic acetal or cyclic ketal. Okay, this is fine. I will manage it on time. Okay. What's this thing? Ketone plus cyanide is cyanohydride. Yeah, not bad. Cyanide is just H plus plus Cn minus basically. So it's no surprise that it adds nucleophilically, right? So it's SN. Sorry, it's acyl nucleophilic addition, right? NHSO3. Okay, fine. So it adds like that, huh? SO4 minus, I would say. So that's also just nucleophilic addition. Nothing special about it. Hey, we have seen some other NHSO3 reagent somewhere, right? What was that all about? Okay, whatever. No time for that. Cool. Then HNR3R4 H plus or OH minus. Right. Yeah, it's also pretty similar. Okay, but this thing is unstable. All right, so okay, this gives this thing. Fine. Tolerance test. So NaNO3 over there, which means NO3 minus. Right, that's about correct. So this Ag2O, oh, this still reacts plus NH3. Hmm. Ag2O you say. So Ag plus over there and O2 minus. Why? I mean AgOH would be correct, but you have AgO. Okay, Ag2O over there. Why? Why is that the thing? You would have NaNO3, yes, but why is this Ag2O? I don't get it. Okay, so actually, like, yeah, nitric acid, the conjugates of that, that's like a good oxidizing agent. So maybe that's why it's doing this. Fine. So it somehow reacts to get this thing. And then this Ag2O solid reacts with NH3 and H2O to give this thing. Okay. Fine. So the whole thing is just the Ag over there. Fine. So what's happening is you have an aldehyde. Ag plus is converting to Ag0, which is Ag metal, right? Silver metal, by a loss of the electron. This species is converted to this. Okay, so the Ag plus, it just gets an electron from this, right? Okay, so I imagine it as Ag plus getting coordinated with oxygen and then the bond breaking homolytically, right? And that will give us this thing. Cool. Yeah, that looks really cool. So that's what's happening. Okay, then OH minus over then they got O radical. Huh. Well, this is weird. Okay, so oh, this is weird. The hydrogen goes from there to there. It's a bit of a shift. And then OH minus, so this is gone. And then a loss of the electron gives us this thing. So it's a single electron. Once again, I just imagine it as Ag plus getting coordinated to O minus and then the bond breaking homolytically, so giving a radical on the oxygen, and that combines with the carbon radical. Okay, and then treated with OH minus gives this thing. So you have converted the aldehyde to what's this, acid, right? Carboxylic acid. And at the same time you have formed silver metal, and the formation of that silver metal is what we actually call as tolerance test. Yeah, so ketones don't do this reaction, obviously, because they don't have that hydrogen over there. Cool. Valence test. Okay. Rochelle salt. This gelated thing is what we use. So essentially just using copper 2 plus. Okay, the mechanism is not completely known, but this is the most possible path. So first is just ionizes and then HOH, which means with water it gives fine, and then copper 2 plus attaches with a carbon over there. Okay, not the oxygen, the carbon. This is okay, this is weird, but whatever. And then it breaks homolytically to give copper plus and that radical over there. Then another copper 2 plus comes in, and you have the same thing once again, right? And after that you have this cation over there. Cool. And then you have an hydride shift. Cool. To give an acyl cation, and then plus OH minus gives this thing. Okay, so you are converting an aldehyde to a carboxylic acid, and meanwhile you are converting Cu2 plus to Cu plus. This is somehow it's like similar to something I've seen somewhere. Yeah, Steinmer's reactions. There as well you converted Cu2 plus to Cu plus. Yeah. Well, whatever. So the basic thing is that you converted. Yeah, you formed Cu plus over there, right? Which would be a different thing. So that means this test works on that basis. Okay. So ketones cannot do this. Cool. All right. Uh, oh, so once you know that it's an aldehyde, you can apply this test to know whether or not this hydrogen over there is there or not. Okay, that looks cool. Right. Halogenation of alpha hydrogen containing carbonyls. Right, that's about correct. This is a nice mechanism. So basic medium is very simple. What about the acidic medium? So it's an alkene. That's why I can do that. Okay, in acidic medium, when you tautomerize the thing, you get something like this. Okay, right. In acidic medium, E1 will basically make you have this enol over there, and then that with X2 gives this. Right. But since there's just so much of water around here, why wait for the X minus to attack when you can just have the water attack it? Oh wait, why even the water? You already have an OH over there. Okay, that's why this is happening like that. Oh, that makes sense. Fool. Right, that makes a lot of sense. Cool. Okay, cool. Next. Fine. Carboxylic acids don't internalize readily and cannot do this properly. Okay. Why do they not enolize carboxylic acid? Oh, okay, that makes sense. These won't enolize. Yeah, that's about right. If you try to put H plus over there, it will just form an acyl cation, or if you try to put OH minus over there, it will just deprotonate the acid. That's it. It won't go any forward than that. Okay, cool. Haloform formation. Yes, this I think I have seen somewhere. Right. So OX minus, that's what we are using. Good. So OH minus over there, I use this thing. Oh. Right. So as we saw, we can use NaOX to halogenate as well. So first of all, OH minus enolizes this thing, then NaOX, it adds the halogen. Okay. Then once again the same thing, OH minus NaOX, OH minus NaOX, it does this thing. After that's done, you do SNAC and this happens. Cool. Yeah, that looks correct. There was some other way of haloform formation as well, right? Well, I forgot that, but whatever. Yeah. Cool. Yeah, this looks cool. Fine. Aldol Edition. Okay, it analyzes first of all, and then some ketone over there it adds to that. Right. Looks straightforward. In acidic medium, just protonate this thing, and it's the actual enol over there. It's still the same thing. Okay. Aldol condensation. So once you do aldol addition over there, okay, you have converted this to that, and after that, all right, so you remove the H and OH over there to give this thing. Cool. Yeah, this looks nice. This looks nice. Oh, acidic medium. So this works in basic medium because that hydrogen is acidic. Okay. And in acidic medium because that OH group. Yeah. So that's aldol condensation. Cool. Okay. Fine. Cannizzaro reaction. Oh, yeah, this thing has that hydride shift over there, which, yes, this thing. Yeah. Right. That makes sense. Cool. So there is in fact hydride shifts over there, and after that it does something like that, and yeah. So it's kind of a disproportionation reaction. You could do something like an, yeah, something like no, that won't work. It won't work. You have to take out something to enter the next molecule, and that would be hydrogen in this case. Yes, that makes sense. Cool. So the hydrogen transfer occurs something like this. These collide, and while these are colliding, the hydrogen gets transferred. Hydrogen never exists in solution by itself, right? So hydride, I wanna say. Cool. Okay, that's nice. Fine. And this is some of the kinetics, right? So you can verify these kinetics on Wikipedia, and I derived it myself. So I don't need any kind of verification. Right. This makes sense, right? This makes sense for the rate law to be like this. Okay, next. Anhydride formation, huh? Okay, fine. Yes, PCl3. This, I've seen it so many times. Right, it just forms, yes, it just forms acyl halide. The reaction is in fact pretty straightforward. Right. Kick out the, yeah, so using the oxygen, attack phosphorus, kick out the chlorine, use the chlorine to attack. Right. Or maybe don't use the chlorine to attack. This also works fine. Yeah. Cool. Yeah, right. That's fine. That's about correct. Yes, this looks correct. Fine. Same thing with PCl5, SOCl2, etc. instead of PCl3. Okay. 14th. Okay. This reaction is in fact reversible. Yes, as we can see, it's a reversible reaction, and it depends on which reactant you are taking in excess. Yeah, that will give us the, if you are taking ammonia in excess, it will give us the right hand side product. If you are taking H2O in excess, it will give us the left hand side product. Whatever. Decarboxylation and decarbonation. Okay. Yeah, no big deal. Decarbonation of fine, fine. Hell Holzar Hens Zens whatever this thing Zenli reactions. Okay. Ah yes, so reaction 7. Where is it? Reaction 7. Halogenation of alpha hydrogen containing this guy. Ah yes, this thing. Cool. So it's not that the acyl halogen is anyway special. The alpha hydrogen, that's the special thing over there. Okay, and that with H2O, just SNAC gives this thing. Cool, cool. Okay. Instead of saying H2O, I should really just say OH minus, because X does not have that lone pair donating ability, so you cannot do the base catalyzed thing easily. Cool. Next, Tabi's Polyphonation. Ah yes, this thing. That was very weird at first. So you have this thing, Tabi's reagent, that creates this kind of well, what do we call it? I don't know. It looks like an alkene, except that tin is the one double bonded to that thing. Okay, and then after that, this is what's happening. This is very bad. I don't know. It's like a complicated mechanism, but really, it's very similar to what happens for Halide, right? Except that you don't have that alkene over there. You have a ketone. Cool. Hey, in Halides as well, it was never an alkene. It was a ketone. Ah, yes. Doesn't matter anyway. Okay, fine. And then oh, so for chlorine this is a little different. For chlorine, that will get kicked out, so you will get this as the final product. Fine. Wetting reaction. Ah yes, that's what I was talking about. The Halide over there. It was the ketone, in fact, right? Imine hydrazone formation. Okay. All right. Cool. Fine. So in basic medium, this is what's happening. You have this kind of equilibrium. Okay. Right. So in the end, it is an equilibrium. It doesn't matter what bond strength or anything you have. The if you put more RNH in the reaction mixture, you will get the right hand side products, the lower products, the correct products, right? Okay, acidic medium. Pretty much the same stuff. Here too, you have to either remove one of the products you get or put more of the reactant or something like that. Removing the product is always a better choice. Okay, Fishner reduction. Ah yes, this is a popular one. So first of all, you will form a hydrazone, and then after that hydrazone is formed, yes, you will just hydrolyze this thing. Correct. So hydrolyzing using basic medium in this case. Looks about right. Yeah. And then it just goes as N2 and you get this thing. So in Fishner reduction, it's very much similar to the Clemmensen reduction, that you are removing the carbonyl and you're not doing anything to other things, right? I don't know how this works on other things, but it definitely does work on carbonyls. Okay, so yeah, that's it. I will put another video. Okay, see you later.